Okay, welcome class to our session for today. So this is the design of steel structures. I am Engineer Ronjan Argami. So we'll discuss the effective area relative to tensile members. So the effective area. The performance of the tensile members is always influenced by the manner of its connection. So last time we have computed for the effective net area that is somehow multiplied to a certain percentage. So the measure of such influence is called the joint efficiency. So it is associated with the ductility of material, the fastener spacing, the stress concentrations on holes occupied by the bolts, the fabrication procedure, the shear lag. Well, the shear lag is actually the unequal distribution of shear, like if we have only one leg of an angle is bolted to a certain gusset plate. The connected element would become overloaded where the unconnected part is relaxed, so meaning it's not fully loaded. So this wherein we can apply the reduction factors. That is why in our previous sessions we have multiplied some percentages of getting the effective area. So percentages multiplied by the net area. So here's the example of that shear lag, wherein as you can see, not all the member elements were fastened to the plate, wherein the reduction factor for bolted connection is given by the equation that the effective area is equal to the net area times this reduction factor U. So we have witnessed that in our previous session as mentioned. While for welded connection, instead of having A sub n, or the net area, we will refer to the gross area multiplied by this reduction factor. In the welded connection, we are not actually having a hole in it, but it is just welded on the edges of the connected member. AISC D3 Table D3.1 provides the rules for determining reduction factor U. While it provides the reduction factor, so the following rules are: first, we have the general category. So this is for any type of member except plates and round hollow sections with L is greater than or equal to 130% of D. So in a while we will discuss on what is L and what is that D. So there are also provisions for the reduction factor in terms of the plates involving round hollow steel sections, again with L greater than or equal to 130% of D, and then alternative values for the single and double angles. So double angles is the combination, or what we call the build-up sections. We also have a reduction factor, alternative values for W shape or the wide flange shapes, the M, the S, and the HP shapes. So for the first provision on the calculation of our reduction factor, we have the general category for any type of the member. Again, we have the exemption for the plates and round hollow sections with L greater than or equal to 1.3D. So we have this equation. So this is the general category wherein the reduction factor U is equal to 1 minus X bar all over L. X bar is actually the distance from the centroid of the connected area to the plane of connection, whether it's a plate or another build-up shapes or rolled steel shapes, while that L is the length of connection. So let us have here some figures to illustrate those variables. So in letter E, of course, that angle bar is actually connected to a plate wherein the connection is along the plane of that plate, and here is the centroid of that angle bar, and that distance X bar is from the centroid up to the plane of connection. Similarly, for the wide flange here, so this is the plane of connection because it is being sandwiched or gripped by the plate, and of course this will be the centroid of angle bar at one side. Hence we have this distance X bar. So if we have the connection that is within the flange, therefore the line of connection or the axis of connection will be horizontal, and this is the line wherein this is the centroid on one side or the upper fiber referring from the neutral axis, and therefore this is the X bar. So finally, for the build-up section channel, so this is the plane of connection from the plate along one side or the left side of our channel bars, and hence this is the centroid and the X bar. So I think that plane of connection shall be adjusted towards right along that side. Okay. So the length of connection L for bolted connection, if we have here an angle connected to a plate, so this is the section and this is the tension member connected to a gusset plate, hence we have here 3 rows of bolt. Therefore the length of connection is from the center to center of the far ends of the bolts. So if we have a staggered spacing of those bolts, of course we will consider still the longest far end distance from the center of the bolt. So for welded connection, if we have a plate connected to a certain member, of course we refer to the length of fillet L, the weld fillet L. And if we have unsymmetrical weld fillet along the longitudinal direction, there will be two values of L, namely L1 and L2. Hence, we can get the average of those fillet length. So let us move on to the calculation of our reduction factor U. Say we have here a round hollow steel tube that is connected to a plate which is located at the center. So notice that we have the outer diameter of this hollow steel section, while the length of connection is the lap between the round hollow steel section and the plate. If the condition is that if the L is greater than or equal to 130% of your outer diameter, then we can just conclude that U, or adapt U, is equal to 1.0. Otherwise, if your L is within the range of D up to 130% of D, we will use the general formula. U is equal to 1 minus X bar all over L. Again, we refer to the centroid of the member connected to the plane of connection. Hence, X bar is computed with the formula the diameter all over pi. Another calculation, if we have a rectangular hollow section with the dimension, the width B, and the total depth H. So what we do is to compare first your L with that of the overall depth H. If H is greater than or equal to H, we compute the general formula U is equal to 1 minus X bar L. And the X bar is computed by that formula, B squared plus 2BH all over 4 quantity B plus H. So what will be our calculation if your L will be within the value of H? Of course, we'll go back to the general formula, U is equal to 1 minus X bar all over L. Only that we stick the value of the X bar of that cross section, not by this formula given here. Similarly, if we have a rectangular hollow steel section wherein the plane of connection is outside your hollow steel section, so outside the perimeter of your hollow steel section, just the same, if your L is greater than or equal to H, your reduction factor U will be the general formula, U is equal to 1 minus X bar all over L. So we have a special formula for X bar is equal to B squared all over 4 B plus H. Again, if your L is within H or L is less than H, we'll just have to use the general formula without applying this special formula X bar given here. So we'll go back to the X bar of your hollow steel section. So another condition, when we have plates, so remember that plates have a single element because unlike angles or angle steel sections, it has two axes. So for plates, we have single plane axis. That is why generally the reduction factor for plates is 1 since it has one element. But there will be an exception for this rule. For members with longitudinal welds on each side without weld on transverse side, such as this one. As you can see, the weld fillet is only on the longitudinal axis of the member plate. So in this case, we have the longitudinal and transverse. Again, there will be no weld on the transverse axis. So what we do is to compare your L with 2W, wherein W is the width of the plate. So if ever that L will be greater than or equal to 2W, our reduction factor U is equal to 1. And for comparison of 1.5 2W to that of the L, within that range, your U will be equal to 0.87. And finally, when W is less than or equal to L up to 1.5 W, your U is equal to 0.75. So we also have an alternatives. Instead of using the general formula U is equal to 1 minus X bar L. By the way, these alternatives are only applicable if your cross-section is yet to be determined. So it is actually a rough estimate of the value of the reduction factor. For single and double angles, we have two conditions. For 4 or more fasteners in the direction of loading, we should consider U is equal to 0.8, while for 3 fasteners in the direction of loading, our reduction factor U will be equal to 0.6. So we have here the illustration. The first illustration, we have 3 fasteners. So we consider our reduction factor to be 0.6. And if we have 4 or more fasteners along the direction of the loading, we have U is equal to 0.8. So we also have alternatives for W, M, S, HP or T's cut from these shapes, or what we call structural T or split T, connected through flange with 3 or more fasteners in the direction of loading with a width at least 2/3 of the depth. So there will be a ratio between the width of the flange to the overall depth. So in that case, we use the reduction factor U is equal to 0.9, then connected through the flange with 3 or more fasteners in the direction of loading with a width less than 2/3 of the depth. You just have to use reduction factor U is equal to 0.85. And if we have your connection plane on the web itself of the flange with 4 or more fasteners in the direction of loading, we're going to use the reduction factor U is equal to 0.7. So here's just the simple illustration. Reduction factor U calculation. So we'll just have to get the ratio of the width of the flange to the depth is equal to 0.82 greater than 2/3, or that is U is equal to 0.9. So we have two examples. So just remember that on wide flange, this is our width of the flange, and this is our overall depth. And so here will be the web. So I'm sorry. It should be the flange. So the outer fibers are what we call flange. And the stem of the flange section is actually the web. So this is another condition wherein the ratio of BF, or the width of the flange, to that of the depth is less than 2/3, then we use 0.85. So as you can see, the connections are within the flanges. Now, if we have the connection that is located on the web itself, then we will use the reduction factor u is equal to 0.7. So let us take this as our sample problem. In here we have an angle that is connected to a plate, and this angle is L6 by 6 by 1/2 thick. So we use 5/8 inches bolts, wherein the spacing of these bolts along the direction of the loading is 3 inches. So here's the cross section. Hence, we need to get your X-bar, or the centroid, from the plane of connection, that is 1.67. So where did we get that one? Of course, that can be found again through the ASTM A36 table, wherein we have here L6 by 6 by 1/2 inch thick. So we can see here that the value of our X-bar and Y-bar are just equal, since we have equal legs for that angle. So we need that value, and of course the area in square inches. So with that, we can now compute for the net area, just like what we did previously. The net area is the gross area minus the thickness 1/2, and of course the nominal bolt diameter. We'll just add 1/8 to the 5/8 inches bolts, and then multiply it by 2, since we have 2 bolts per section. So that would yield to 5.02 square inches. So with that, the length of connection is 3 plus 3 is equal to 6 inches. Now, comparing L with that of your X-bar, of course, 6 is greater than X-bar. Hence, we can use the general formula 1 minus X-bar all over L. So with this, you just substitute the value of your X-bar 1.67 and your L 6. Therefore, we have a reduction factor equal to 0.7217, and that shall be multiplied to your net area to get the value of the effective area. So 5.02 times 0.7217, and that would equate to 3.623 square inches. So applying now the alternative that was presented a while ago, we have here for 4 or more fasteners in the direction of loading. We use 0.8. For 3 fasteners in the direction of the loading, we use 0.6 as a reduction factor. In this case, we have actually 3 rows of fasteners in the direction of loading. Hence, we use the reduction factor U is equal to 0.6. So, applying that, you just have to multiply to your nominal area or net area. Hence, we can get the value of 3.012, and that is actually less than the value when we use the general equation U is equal to 1 minus x bar all over L. Hence, we have here the note, either U is acceptable, U value is acceptable, so both of those are acceptable, but the specification permits the larger one to be used, meaning the larger one that we have obtained is using the formula U is equal to 1 minus x bar all over L. That is why the general formula is more accurate than this alternative value. Finally, the alternative values of U can only be useful during preliminary design, as I mentioned, when actual section properties and connection details are not known. Hence, this is more accurate to use if your sections dimensions are known. So that's all for our session for today. See you next time for more examples and another topic. Thank you, class.